Now we move from agents that can see the blockchain to agents that can use it. Smart contracts become callable services. Agents read state, interpret ABIs, and safely trigger transactions through a wallet to interact with real dApps. So far, we've built the path from agent fundamentals to Web3 connectivity, planning, tool use, memory, wallets, signing, RPCs, and SDKs. At this point, the agent can read blockchain data. The next leap is action, understanding smart contract ABIs, choosing the right functions, and calling them safely before moving into testnet experimentation. Think of a smart contract like an API that lives on a blockchain. It has an address, defined functions, and internal state. To use it, an agent relies on RPCs, SDKs, wallets, and the ABI to understand what can be called. Read calls are simple queries. They inspect state and usually need no signature or gas. Writes are different. They prepare a transaction, require a wallet signature, pay gas, and wait for blockchain confirmation. An AI agent does not talk to a smart contract directly. It works through an interaction stack. First, reasoning logic decides the goal. Read data, prepare a transaction, or call a function. Then SDKs like ethers.js or Web3.py turn that intent into a valid contract call. If value or state changes are involved, a wallet signs the transaction. Finally, an RPC provider relays it to the blockchain, where the deployed contract executes the request. The ABI is the contract's operating manual for software agents. It tells the agent which functions exist, what inputs they expect, what outputs come back, and whether a call reads or changes state. With that definition, the agent can turn a request like balance off or transfer into properly encoded call data, then decode the raw response into meaningful results. Without the ABI, the contract may still run, but the agent is mostly guessing at the language. Inside the ABI, each function entry defines a possible tool call. The inputs tell the agent which parameters to supply, and in which types, such as an address recipient or a uint 256 amount. The outputs tell the SDK what to decode from the response. State mutability shows whether the call only reads data, computes locally, accepts value, or changes state. Getting these fields right prevents malformed calls and failed transactions. Contracts also use the ABI as a reporting format. When execution emits an event, like a token transfer, the ABI tells an agent how to decode that log into meaningful fields. That lets the agent monitor activity and trigger workflows. If a transaction fails, custom errors provide structured failure data instead of a vague revert. Decoding both events and errors gives agents better observability, so they can react faster, explain failures clearly, and operate more reliably. For an ABI to be useful, it must match the exact contract address and network your agent will call. Prefer trusted sources, verified explorers, official repositories, SDKs, or deployment artifacts. Also check whether the contract is a proxy, and use the implementation ABI when needed. Before any transaction, confirm the chain ID, address, expected function, and source provenance. Unknown or mismatched ABIs should be treated as execution risk, not just missing documentation. A read call is how an agent asks a contract a question without sending a transaction. View functions inspect existing state, such as balances, allowances, prices, or configuration. Pure functions only compute from their inputs, without reading chain state at all. In both cases, the request is handled locally by an RPC node, often through ether call. Because nothing changes on chain, the user does not sign anything, and no gas is paid from their wallet. Here's a typical pre-flight check. Before recommending a token transaction, the agent reads balance of to confirm the wallet has enough tokens, then reads allowance to confirm the spender is approved for the required amount. No state changes happen yet. These results simply guide the next step. Proceed, ask for approval, or warn the user. Write calls are where an agent changes blockchain state. It starts by choosing the contract function, such as transfer, approve, swap, or mint, then uses the ABI and inputs to encode call data. Next, it estimates gas and prepares the transaction. A wallet must sign it, because state changes require authorization. After broadcasting to the network, the agent should track the transaction receipt, confirm success, and handle failure cleanly. Before signing, the SDK turns intent into an exact transaction request. The toField names the contract, and data carries the ABI encoded function call. Chain ID prevents sending it to the wrong network. Gas limit caps the execution work, while max fee and priority fee affect how quickly validators may include it. The nonce locks this transaction into the wallet sequence. Value only matters when the function is payable and must receive native tokens like ETH. Once the transaction is built, signing becomes the authorization step. The wallet, or a delegated signer, uses a private key to prove consent without exposing that key. The signed transaction is broadcast through an RPC provider and waits in the network until included, replaced, or dropped. The receipt is the agent's source of truth: status, gas used, block number, and logs. Use it to update state, retry safely, or surface failures. When an agent can initiate contract writes, safety must happen before signing, not after. Treat every write as a pre-signed checkpoint. Is the contract trusted? Is the function expected? Is the chain correct? And is spending capped? Decode the calldata into plain language and simulate the outcome when possible. For approvals, swaps, transfers, or anything irreversible, require human confirmation. The goal is simple. Agents may recommend actions, but guardrails decide whether execution is allowed. You've now seen how agents use ABIs to understand contracts, read state safely without gas or signatures, and prepare write transactions with signing, broadcasting, and receipts. The next step is practice. Use testnets, faucets, and controlled environments until every interaction feels predictable before touching mainnet funds.